Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be looking at episode 6 of our Discovering STM32 series. Today we are going to be getting the code started for the LCD screen on our discovery board. This one right here. So we're firstly going to be looking at getting the hardware all set up and working for what we need for the LCD display. So getting our LTDC and DSI peripherals up and running on the STM32 chip, as well as getting the LCD screen itself initialized, and getting to the point by the end of this video where we can actually get something being displayed on the screen and make sure that the driver itself is working. Over the course of the next video in this series, we'll be looking at getting some of the rendering stuff up and running. So being able to render simple shapes, lines and squares, circles, that sort of thing, as well as a way to be able to implement getting fonts onto there and actually getting text rendering and things like that done as well. So, like I said, over the course of this episode, we want to get the driver up and running for that one and get to the point where we can actually see something happening on the screen, make sure all of that is working correctly. So what I'd like to do first is just start by giving a bit of an introduction as to how the peripherals actually work and how things are sort of laid out and connected with one another before we actually get stuck into the code. Now, bear in mind, what we're looking at today can be used for different types of displays, whether you've got a different discovery board or another board that has a different type of LCD screen. In the case of this particular board, we'll be using the DSI peripheral to sit in between the LTDC. So the LTDC being the peripheral that allows, or basically takes the data for what we want to display on the screen and actually prepares that and gets it ready to send to the screen. And then it will feed that through to the DSI peripheral, which allows it to then be fed to the screen in a way the screen can display it. Now, in some cases, depending on what sort of screen you've got, you may not need the DSI peripheral. I believe it stands for differential signaling interface off the top of my head, and that's the particular method that this LCD screen uses in order to be able to communicate with the STM32. Some screens will communicate via a parallel style interface or other different types of interfaces that you might come across, and the LTDC is pretty flexible in the ways in which it can actually talk to various screens. So it is possible to take what we're going through today and use it for different boards or different LCD screens. But we're going to go with the particular approach for this board itself. If you do run into any questions or anything like that related to any of the other approaches, definitely feel free to drop me a comment and I'll see what I can do to help answer those questions and get us a bit more clarity with those particular situations. So first things first, let's jump over to this one. And let's have a look at how the communication actually works for this LCD screen and the way we're going to be approaching it with our driver today. So essentially the screen that we've got, let's draw him over here. Bit of a rough drawing, but we'll go with that. So the one we're working with has actually got 800 pixels across by 480 pixels high, and the way it kind of is all connected is we have the DSI peripheral, which sends its data out to the screen, and we have the my writing's terrible, LTDC peripheral, which feeds its data to the DSI peripheral. Now, with the data that we're actually going to be displaying on the screen, that is actually going to be sitting in RAM. And one of the things that we discussed during the last episode was actually getting the SDRAM up and running using the FMC peripheral so that we could have enough space to be able to store the data that we need for the screen. Because given the fact that we only have 0.5 megabyte worth of RAM in total on the STM32 F7 chip that we're working with, doesn't really give us enough space to be able to store a higher quality image in the way that we're going to be wanting to work with it on this screen. You could go with a different type of display format, which might allow you to be able to fit, say, a palletized display into the system RAM, but we also want to be using the main system RAM on the STM32 chip for a variety of other things. So in this case, the RAM that we're going to be using will be the SDRAM, which we've got 16 megabytes of that on the discovery board that we're using. And then once this is all set up, effectively what we're going to be able to do is get the CPU to send data to the RAM, so pixel data, which the LTDC will automatically pick up on and feed that through to our LCD display. So we'll put LCD there so we know what that one is. Now, the LTDC does have a few different features that make it really useful, especially for doing simple user interfaces and stuff like that. So it does allow us to actually take two separate layers and blend them together onto the LCD screen. So it does actually allow us to, say, for example, have, just roughly draw this in. So it allows us to have a background color, which is just a solid color for the entire screen. And then we can have one layer of image data, which we'll call layer 0, and then another layer of image data, which we'll call layer 1. And then depending on the alpha value or transparency value of each of the pixels on the various layers, it will actually go through and composite those layers together in order to allow us to have a single image being sent to the screen. Now, one of the reasons why I like to use that approach is that when I'm doing user interfaces, for example, if I'm going with elements of the screen that are fairly static, so aren't changing regularly, I'll typically have those being drawn to layer 0. And then anything that is changing per frame, or that is likely to be updated for each frame that we're rendering, I'll draw those ones to layer 1. Now, the reason why I go with that approach is it means that with each frame that we're rendering, we only need to be clearing and re-rendering one layer, while not having to completely re-render the particular information that is not needing to change on a per frame basis. Hope that kind of makes sense, but when we get stuck into a bit of code, I'll explain that a little bit more, and we'll see it a bit more when we actually start to get stuff being rendered to the display as well. So let's jump over to our display there. Pop that guy over there for the moment. And just got the code here from the previous episode, and just going to start to build the driver up for the LTDC as mentioned. So first things first is, during the first episode of this series, we did go through and actually get a lot of the HAL drivers moved over as we needed to. The one thing that we're going to need in here that we don't have at the moment is some of the code that's supplied by ST Microelectronics that allows us to get this particular LCD screen working. So we can do the stuff to be able to get the LTDC initialized and the DSI initialized, but rather than having to go through and actually write the code to get the LCD panel itself initialized, we're going to utilize that code from ST Microelectronics. Sorry, not enough coffee yet this evening, or too much, something like that. So let's jump in here, and we are going to go into our repository, which will be in our, where are we? Jump into here. In our STM32 cube folder, which will be in your users folder on your computer. And we can see what we're looking at in the first episode, where we've got all of the code and files that are downloaded for the F7 series. If we go into our drivers and to BSP, and we are using a 769i discovery. Actually, it's not what I'm looking for. It's hiding from me. Where are we? Nope, we don't want the HAL stuff there. We don't want that stuff. Where are we? Not seeing what I'm looking for. We should have a components folder hiding in here somewhere. It's not in middlewares. Might be hiding in here. No. I wonder if they've actually changed this since the previous version, or if I'm just being forgetful. It's not in there. Aha, it is in there. So jump into the firmware, go into drivers, BSP, and components. Now, there's a few in here that we're going to end up using over time, but we're going to start with the OTM8009A, which is the particular LCD panel that we're actually using. So we're going to grab that, and we're going to grab common, and we're going to drag these guys. We'll create a components folder in here first, like so. Jump back to this one, and let's drag these guys into there. Tell it to copy the particular files that we want, like so. Now we're also going to have to go into here and let it know to look in those particular paths. And in here, so that will be drivers, components, OTM8009A, include that one. And common, whoops, don't want command, we want common. There we go. Pop those guys in there, and because we're going to be dealing with C files, we're just going to be putting those in here. And might also put them in here as well, just in case. Definitely can't spell. A common theme for these streams. That one there. Going to do the same for our release config. Like so. One there. Chuck them in here as well. Just make sure I've got that right. Drivers components common, drivers components OTM. Yep. Checking that I haven't popped in any silly spelling mistakes in there. That looks good there, looks good there. And we also need, actually we've got our drivers folder in as our source location, so we don't need to worry about that one. Save that, and that's got that bit sorted for the moment. I'm just going to jump over to that one, and let's get our drivers folder opened, and we'll create a header and a source file for this one. So following our same naming scheme that we've been using previously. Source QAD LTDC .cpp, like so. Now we'll grab our header out of here. On there, and rename this guy. Okay, and today's date, 3rd of October. And also do our stuff to prevent recursive inclusion. Like so. Let's copy that one over to here. Get rid of these bits. And we are going to be including QAD LTDC. Now, similar to how we did things with our FMC and SDRAM driver, we are going to be doing this using a singleton class. Again, much like with the FMC, we've only got one of those peripherals in the system, so we don't want to create a class that can have multiple instances because we've only got the one LTDC piece of hardware in there. So I'm going to take a similar approach to what we've done previously. We are just going to pop in a couple of defines and structures and things first up though, before we actually get on to creating the actual driver class itself, which are going to help us to be able to lay out things like buffers and things like that as well. So to give a bit of an idea of how we're going to go as far as our pixel formats and things like that, if we jump back over to see if this one is still behaving for me. Like that. So essentially, we're going to go with 2 layers that each have 16 bits per pixel. And then we're going to break those 16 bits up into 4 sections. So the first section will be our alpha value or transparency. Then we'll have our red, green, and blue value. And then each of these will be 4 bits, which allows us to have a particular value in between 0 and 15 for each, the alpha, red, green, and blue. And through doing that, we can have a fairly decent gamut of colors that we can display. We could turn it all the way up effectively and go with 8 bits per color or 32 bits per pixel. However, we do also want to be able to utilize a decent bit of the SDRAM bandwidth for things like audio and stuff like that in the future. So by going with 16 bits per pixel as opposed to 32 bits per pixel, we're actually halving the amount of data that we're going to be moving around. And that goes for us actually rendering stuff into the buffers in the SDRAM, as well as the LTDC pulling that data back out so that it can then display it onto the LCD screen. Now, the other approach we're going to be taking is for each of our layers, we're going to have 2 buffers in RAM. So there'll be 4 buffers in total. And at any one time, one of these will be the back buffer and one will be the front buffer. The reason we do this is because that way the front buffer will be the one that is getting displayed to our LCD screen. So that's the one that our LTDC is actively taking data from and putting it onto the screen, while our back buffer is the one that we're actually rendering things to. So whether we're drawing lines or text or whatever. The reason why we go with the double buffer approach is because it prevents us from actually seeing things being drawn on the screen. So we can effectively draw it all and then we flip the buffers around. So basically flip the pointers to those buffers so that when we do that, we're seeing the whole frame done in one go and we're not actually seeing the CPU rendering those things directly on the screen, which gives us a much cleaner and much more presentable approach for doing things like user interfaces or whatever we decide to draw to the screen. Similar approach to what we do if we're actually developing a game engine or something like that as well. So if we're doing 3D graphics on a typical computer using a GPU, we'd be going with 2 or more buffers in order to do the same thing. We'd be rendering to a back buffer and then have a front buffer that's currently being displayed onto the screen. So we're going to go through and get our particular structures set up so that we've got everything ready to go for that. So if we jump back to that one there and pull up the bits that I need over here. There we go. All right. So the first thing we're going to pop in here is also going to be including in here the OTM8009A.h file, which is the driver file that we copied across just before. And then we are going to set up some structures for our frame buffers and pixels. So we're just going to call that frame buffer structures. And we'll make a section for our, actually, we'll just go with that for the moment. Now, we're also going to pop a couple of defines in here, which will come in handy as well. So just going to define QAD LTDC width, which is the amount of pixels wide that we've got. And we're just going to set that at 800. QAD LTDC height. Move this guy over a bit. And that'll be 480 because it's 800 by 480 resolution. And QAD LTDC, let's call it pixel count. So this will be the total number of pixels that we've got in total. And that will be QAD LTDC width times QAD LTDC height, like so. So we're using those when we actually go to set the driver up, and also with creating these structures as well. So we're going to create a type def in here, and we'll call that QAD LTDC buffer, just to keep it nice and simple. In some situations, I have actually gone through and made systems where you can control a particular buffer formats and things like that as well, which does add a bit of extra complexity. However, we're not going to do that this time around. So just going to use a uint_t16, so that'll represent each pixel. That'll give us our 16 bits for each pixel. And let's just call it pixel. Like so. Actually, definitely not thinking ahead. We need more than one pixel in here. So it's going to be an array of pixels. So that will be QAD LTDC pixel count, which basically gives us an array of uint16s that contains the amount of pixels that we need. Now, because we're going to go with 2 buffers per layer and do the double buffered thing that I mentioned before, we're going to create another structure, and we'll just call that QAD LTDC double buffer. And in there, we are going to create an array of 2 buffers, which will be QAD LTDC buffer. And let's just call that buffers, and we're going to pop the 2 in there. So this basically gives us a particular structure that gives us access to all of the pixels in both buffers, and makes it a little bit easier for us to be able to access what we're going to need there. Now, we're also going to go through and might actually come back to developing our initialization structure for the moment, but we're going to take a similar approach with initializing the LTDC class as what we've used previously. So basically creating an actual structure that contains the information that we need to be able to set up the class as we need it at that point. So again, that'll make a little bit more sense once we get to that. Thinking of too many things at once at the moment. All right, so let's just call this QAD LTDC. Again, going with QA for Quartz Arc, which is the project name, and D for driver. So sticking to our naming structure that we've been using previously. Now, there's a few constants we're going to throw in here, which is going to help us to get things set up a little bit. Prior to that, however, let's go through and structure this so that it's going to act as a singleton class. So first things first, our default constructor, we're going to have to make that one private, which will be QAD LTDC, like so. I'm going to go and delete our copy constructor. So delete that one. And if you've watched the previous episode where we get the FMC up and running, you'll recognize what we're actually doing here, because it's basically the same approach. So operator equals, so going to get rid of our assignment operator as well. QAD LTDC other equals delete. And then we're going to go through and also create a get method as we did for the FMC class. Brain is definitely not working right now. Like so. And then create a static instance there, and we're going to return that like so. There's a fair few bits and pieces go into this particular one, so let's go through and start getting our actual initialization methods sorted out. So there's a few different things that we're going to have to pop in here. Inside this class, we're going to have our initialization and de-initialization methods, of course, so that we can get the peripherals and display up and running, as well as de-initializing them if we need to be able to do that. We're also going to be doing some things to be able to control the LCD itself, so to be able to turn it on, turn it off, and control the brightness of it. Also going to be going through and providing some methods to allow us to get access to the buffers themselves, which are going to be managed within the class. So we'll start with our initialization methods. I'm just going to call that one init, and I'm going to need to be able to pass that a little bit of information. So we might go ahead and create the initialization structure for that. Actually, we might take a slightly different approach. Might simplify things a little bit. Let's just make this a void method for the moment. The code from this video will also be available on GitHub, much as with the previous episodes as well. So feel free to jump on there and download that if you're interested in having a bit of a look at it or trying it out. Now, we're going to do things similarly to the FMC driver class as well, in that we're going to have a bunch of static methods that then connect to non-static implementation methods, which is why we're going with imp underscore for this one. So I'm going to go use get imp init like so. And we want one to be able to de-initialize as well. That one doesn't need to return anything. Oh. There we go. Mouse keeps disappearing. There we go. And we'll create a private section down here to be able to pop those implementation methods in. And for this one, it will be QA results imp underscore init. So be returning a QA result, but we don't need to pass it anything. We could go through, like I've done previously, and actually provide it with what pixel formats and how many layers and what our background color and all that sort of stuff is when we initialize it. However, when we go to set up the driver for this one, we're going to do it so that we're going to be using 2 layers regardless. We're going to stick with our fixed 16-bit per pixel format, and we might just hard code the background color for the moment as well. So it just keeps things a little bit simpler because we can always add to that at a later date anyway if we wish to. So that's our initialization and de-initialization methods. These ones we are going to pop over in here in our CPP file, and they will be QAD LTDC initialization methods. Like so. And we know that if we get to the end of this one, then everything is all good, so we can return QA-OK at that point. We'll pop all our initialization code into there. Might just make a note in here that these will be our initialization methods, just to help tidy things up a little bit. And let's go through and start getting this initialized. Now, as far as the DSI communicating with the LCD screen, we don't need to set any GPIOs up for that specifically because the DSI uses its own pins. We do need to go through and set up a couple of GPIOs, however, to be able to control the backlight of the LCD screen. So we have one pin that we're going to be using for that. And there's also another pin that allows us to do a hard reset on the LCD screen itself, so that that gets reset whenever that pin gets toggled effectively. So that way, if we need to go through and reset the screen, whether we're doing it during the initialization process or if there's something that we're doing with the screen that needs us to be able to reset that partway through whatever we're doing, then we'll be able to do that. So let's get those GPIOs set up first up. So init GPIOs, we're going to need a GPIO init type def for that one, and we're just going to call it GPIO init and fill it with zeros. We'll do our backlight pin first. Now, the other thing that we might do is just pop in the details into our setup file of our pins there. So let's go into here and we're just going to go LTDC. And just so that I know exactly which ones I'm going with. Copy and paste these over to this one. Rename these guys. Just name that so it's a bit more consistent with how we're naming the driver. All of these pinouts are in the discovery board documentation as well, but rather than going through and actually looking those up, I'll just copy and paste those from my previous code. Make things a little bit quicker. If anyone wants a bit more of an insight into approaches to finding particular bits of information in the documentation, I'm more than happy to sort of have a bit of a look into that. We could do like a separate video on that if people are interested, so feel free to let me know if that's something that you'd like me to do. And we're just going to go through and QAD LTDC, oops, LTDC backlight pin. We want our mode for that one will be output push pull. We are going to use the pull down resistor on that one. And that's so that by default, before we actually do anything with the pin, it's actually going to be keeping the backlight turned off effectively by pulling the signal down. And set the speed for that one as well. So get that one initialized. So that's that one, and we're just going to copy and paste this for our reset pin as well. That one's also going to be output push pull. However, we're going to go with a pull up on this one. The reset pin for this is active low, which means that we want to use the pull up resistor to hold it high so that it's not resetting unless we're actually asking it to, in which case we can pull that pin low to be able to do that. So there'll be a reset port. All right. Now that's got our GPIOs done. The next step that we need to take a look at with that is actually resetting the LCD panel itself, which we're going to do using that reset pin that we've just set up there. So for that, we're just going to use our GPIO write pin. And that will be QAD LTDC reset port, QAD LTDC reset pin, and GPIO pin reset to pull that one low. We're going to pop in a delay in there, just 20 milliseconds, just to give it time to perform the reset. And then we're going to pull that pin high again. So just GPIO pin set, and then we'll also throw another 10 milliseconds delay in there after that, just to make sure that reset process has occurred correctly. So that'll get our LCD, our actual LCD controller on the screen itself reset. The next thing that we need to do is get the clocks initialized for both our LTDC and for our DSI peripheral. So for that, we're just going to go HAL RCC LTDC clock enable, and just make sure that those clocks are actually reset as well. LCD force reset, and HAL RCC LTDC release reset. And I'm going to do the same thing for the DSI clock. I'm just getting it enabled and then going through the process of actually resetting it like so. So that's our peripheral clock sorted out there. Now, we also need to set up the PLL for the DSI, and then we can go through and actually get the DSI peripheral set up. So it's going to need to know sort of what sort of timings and things like that as far as the data that we need for the communication between the STM32 and the LCD screen. And to help us with that, we might look at doing a little bit of copy and paste there. However, there's a few bits of information that we want our class to also hang on to for us. So let's pop that in here just before our default constructor for the class. And we are going to need to pop in here our handle. So we're going to need our DSI handle type def. And we'll just call that m_s DSI handle. And LTDC handle type def for our LTDC handle. So using the same naming convention that we've been using. So m_ to denote that it's a class member, and then the S because what we're actually creating here for both of these guys is a structure, effectively. Now, I don't think there's anything else that we're going to need to pop in there for the moment. Let's just double check that. What have we got here? Also going to pop another handle in here as well, which will be our DSI configuration handle. So that one there, we'll just call that DSI config handle, like so. So much as we've seen with the previous drivers, those handles are just used to allow the HAL to be able to help us get some of that stuff set up. So for some of the methods that we're going to be, or some of the functions that we're going to be using from the HAL, they're going to need the handle to know what peripheral they're working with and get access to it, things like that as well. Now, might help if I actually type this in correctly. Like so. Now, let's grab that and we'll pop this in here. There's a fair bit of stuff that goes into actually initializing the DSI itself. So firstly going through and making sure that it's de-initialized. We're going to set up the DSI PLL so that the DSI is getting the correct clock for it to be able to operate. Telling it how many lanes of data we're actually using to communicate in between the DSI peripheral and the LCD screen. We also want to make sure that we're giving it the correct clock information there as well, and then just going through and getting the base of the DSI initialized. We also need to go through and set the DSI configuration so that it knows what sort of timings and things like that as far as the communication with the screen. So we can see here that we've got our horizontal and vertical active periods, and then our front and back porches in there. Now, initially, if you haven't messed with screens that much, or if you've only dealt with sort of certain parallel LCD screens with microcontrollers, that sort of stuff may seem a little bit confusing. So to help explain that, let's see if we can jump back to this one here. So essentially what the DSI will be doing is streaming a bunch of pixel information to the LCD screen. Now, if we have a look at the actual information that's being sent, so we imagine this inside box is actually our LCD screen. And then what the DSI is going to be doing is sending streams of data where it's going across horizontally. So basically scan lines, like so, and then sending each pixel value as it goes. Now we also have what are known as our front porch and our back porch, which are basically areas where we're not actually sending any actual pixel data per se, but it's required in order for the LCD controller that is running the screen itself to have the particular amount of time that it needs to internally set itself up for that data to come through. So it has that front porch so that it has that bit of breathing room to get everything prepared prior to us getting to this point here, where it's actually starting to send pixel data. And then we send all of that pixel data with those horizontal lines, get to this area, and then it needs that bit of timing in between there and there in order to kind of be able to finish what it's doing, I guess is the best way to describe it. So this is our vertical front and back porch here and here. We also have our horizontal front and back porch as well, which again is basically just giving the LCD controller the time that it needs to be able to get things done correctly there. So again, front porch and back porch. So that can be a little bit confusing. It's probably easier to understand if you've ever gotten into the way CRT screens worked with the old big chunky screens back in the day. Similar sort of process, but it's done for different reasons because it's actually something that the LCD controller itself is using in order for it to internally get things done correctly. So let's jump back to that one there. So as we can see, we're basically setting up a few things here as far as our values here. So our active period is the amount of pixels that it is active for. So we're horizontally active for 800 pixels, which is the amount of pixels that the screen is actually, its width. And same with the height. So we're going to be active for 480 pixels in height. And then basically setting the amount of pixels that vertical sync and our front and back porch are going to require for those timings to meet what the LCD controller needs for that to happen. And this is going to be different depending on what LCD screen and thus LCD controller is actually being used by the physical LCD screen itself, separate to the STM32 that you're using. So basically going through and filling out a bunch of the details that we're going to need so that the DSI knows how to communicate with the LCD controller itself, including letting it know what sort of format we're using to send the data for the actual pixels. So in this case, we're using 8 bits per color, so 24 bits per pixel. We're letting it know that the vertical sync and horizontal sync signals are active high. So vertical sync and horizontal sync are what allows the DSI to understand where it is in the stream of pixels that are being sent per frame. So as it's going through, like I showed in the diagram, and basically going through and filling out those details as needed. They can seem a little bit confusing initially, so I'm not going to try and go into some of that stuff too much. However, again, if people have more questions, want me to go into more depth with some of that sort of stuff, I can maybe make a separate video on that. However, just so that you kind of have an idea of the particular bits of information that we're going to be sending to that. You will find if you're using a different screen, if it's one of the discovery boards that's also using DSI, a different one than what we're using here, you will find in the examples from ST that there will be the required information. You'll be able to find where it's actually going through and configuring the DSI in the example, and you can basically pull those required values out of there, which is where these ones have actually come from. A couple of years ago when I first started using these boards, basically pulled some of that code out, reformatted it, and got it set up the way that I wanted it for my code. Now, there is also a couple of other values that we're going to want that need to be popped into our driver class, which is our lane byte clock and our LCD clock rate. So we're going to go through and pop those in here. And these are just going to be constant values. So let's pull those ones up on that screen there. So we're going to need, I think these guys, UINT32s. Need our LCD clock rate, which will be, what's that, 27,429. And this lane byte clock, that's going to be in kilohertz, so we might just make a note of that just so that we know. Tidy that up a bit. And we're also going to need, get rid of that underscore, and our clock divisor, which will be 15,625. Okay. So that'll give us what we need for the moment. And just to make sure that we haven't missed anything, let's just see if that wants to build for us. Definitely errors there. Where do we go? Aha. Straight away off the top of my head, I know what I missed. So we need to let the compiler know what these methods belong to. That would definitely help. Like so. That should hopefully build for us. No, still errors. Might help if we go with the names that we're using there. Fix those guys up. The joys of copying and pasting from a different project. And it doesn't know what that one there is. Let's double check. Underscore SDSI. CFG handle. There we go. And looks like we have it building. And 0 errors, 0 warnings. All right, so that's got our DSI initialized. So now what we're going to have to do is go through and actually initialize the LTDC peripheral, and then we can actually get the layers initialized as well. So For each of those, we're basically going to be filling out a structure full of the required details and then getting each of those initialized, get our layers enabled, and then we will create a couple of tool functions or methods that allow us to turn the LCD on and off and control the brightness. And then at that point, we should be good to be able to test that we're actually getting something showing up on the screen. So the stream's behaving itself, which is awesome. So again, here's one I prepared earlier. And so basically letting it know that we're using the LTDC peripheral, providing it with some of the timing details similar to what we've done for the DSI. Because the LTDC also needs to make sure it's getting its timings correct. Letting it know what the width and the height in pixels is of the display that we're working with. So if you're using a different display, they're going to be different values. I think there's another discovery board, F7 discovery board, which has a slightly different LCD screen. That one has a smaller resolution than this one, so you'd need to be aware of that if you were working with that one. And same for any of the other LCDs that you might be working with. So even if you were using, say, a parallel LCD screen rather than one that's using the DSI, then you'd be wanting to make sure that you're using the values necessary for that. So again, have a bit of a look at the examples for the particular board that you're going with. We're initially just going to set our background color to blue, so set our red and green to 0 and our background to 255, just so that if we see solid blue color come up on the LCD screen, we know that we're getting our initialization working. We can come back and mess with that just to test it as well. And then creating a structure from our video config. So it's actually taking the DSI config that we've created up here and then filling out the required details from that into our LTDC handle, and then using that handle to initialize the LTDC itself. And then we'll go through and get our layers initialized. So init layer 0 and init layer 1. And for these guys, again, just going to copy and paste this. Like so. So for each of the layers, you can have a layer that doesn't fill the entire display. So even though we've got 800 by 480 pixels, you can have a layer that's set up just to work with a particular part of that. So say if you wanted to create an area of the screen where that's where you're going to be drawing to and the rest of it's just going to be the background color, you could do that. And you can do that independently for each of the two layers. What we're going to do in this instance, though, is we're going to have both layers fill the entire screen so that we've got them being composited on top of each other for all of the pixels. So setting the start, the origin as 0 and 0 for the X and Y coordinates, or the width and the height there, letting it know what the end point is for both of those. So that'll be 800 and 480 respectively, because that's the size of our display. Going to change this one here. So we're actually going to be wanting to specify the particular pixel format there. So if we jump into our LTDC file, we'll find our pixel formats. Now we've got a few different pixel formats available. So we do have the 32-bit per pixel that I mentioned earlier. However, we're going to go with the 16-bit per pixel, which will be this one. There is also a couple of other 16-bit formats as well that we could use. I like using this one simply because it allows setting up the data to be a little bit easier, and it also gives us a bit more ability to control how much transparency there is per pixel. So if we have a look at this format, for example, it's only giving us a red, green, and blue value, although it will give us a wider range of colors than we can have compared to the format we're going to use. We've got this format here, which only uses 1 bit for the alpha value, which means that essentially each pixel on the layer would either be completely transparent or completely opaque, whereas with this one we actually get more ability to control the level of transparency, so any one of 16 different levels for that, which can come in a little handy for some of the stuff that we're going to be looking at. Now, the start address for this layer, we're just going to hard code for the moment. So our SDRAM, as far as the memory map for this board, and the way we've set up the FMC during the last episode, we know that that starts at C0000000. So the start of the very first buffer for that one is going to be sitting at that address. And we can also set a background color and alpha values and stuff for this layer. We're telling it how we want to blend it with the layers that are underneath it. So in this case, it's just going to give us a fairly standard blending using these particular settings. You can have a bit of a play with some of those settings to see sort of some of the different effects and things that you can actually get as far as blending different layers together. And then just telling it what the width and height is of the image itself there. Going through configuring the layer and then turning the layer on so that the LTDC knows that we're actually using that layer. Now we're going to basically do all the same thing for layer 1. So I'm going to copy and paste that. Same width and height, same pixel format. Our start address for that one is going to be slightly different. So if we pull up our calculator here, we know that we've got 800 pixels wide by 480 pixels high times 2, because there's 2 bytes per pixel, which gives us 768,000. Jump into hex, which gives us that same value in hex, and then we can go plus C0000000, which adds our start address for our first layer, and this is going to give us the particular address that we're going to want. Actually, no, because we're double buffering, we are going to want to, let's go with BB800 times that by 2, and then we'll add our base address to that one. Alright, so basically, if we had a look at the memory map, kind of how we're actually going to be laying things out with that, you jump back over to this one. So we've got our base address for our SDRAM, which is our C0000000, and then we're going to have 4 sections in there. So this to here will be layer 0. This 2 will be layer 1. And then we'll have buffer 0 and 1 for that layer, and buffer 0 and 1 for that layer. So we need, as we've just calculated, this address here needs to be offset by twice the size of a single buffer, because we've got two buffer here, and then the address that we've just popped in so that we know where that will be located. Hope that kind of makes sense. So let's jump back to that one there. Like so. Excellent. So that's our buffer start address for that one. I'm going to keep all the same values there, same width and height. However, we're going to tell it that we are dealing with layer 1 there. So fairly similar, just different start address and different layer index for that. Basically gets all of that set up. And nearly have our initialization method all done. So there's a fair bit of stuff needs to be initialized for this one. We're going to enable our DSI at this point because we've got the LTDC and DSI initialized. Now, at this point, that's basically the on-chip peripherals done. We then need to go through and be able to initialize the LCD controller for the actual screen. In order to do that, it needs to have us provide a particular function that the driver can use to be able to send the specific commands it needs to the LCD driver via the DSI. So if we open up our OTM file here, I think this is in the header file. And we'll find this DSI IO write command method. So we're actually going to need to create one of those that the driver can use in order to be able to send the commands through that it needs to be able to do the initialization. So if we have a look in here, in the actual initialization for the display, it's going to go through and send a bunch of commands to the display, the LCD controller, in order to be able to get that initialized. So for that, let's just close all of that. We are going to pop this in here actually. And let's just call this DSI command methods. And for this one, that will be void DSI IO write command, just as we saw in the other file. And it needs to be able to be passed the number of parameters that are getting sent to the controller, as well as a pointer to the actual parameters themselves. Like so. Now we might also pop a declaration for that one in here as well, in our header file. Jump back to here and we'll pop in the code to actually get those commands sent. Now, a couple of different ways that we could do this. Just having a think about the best approach we could take there. Okay. So in order to be able to send that, we're going to need to be able to access the handles that we've created inside the class, which means that we can't put this method directly inside the class, or the driver's not going to be able to see it correctly. So what we might do with that is actually create a method in our class itself. So that'll be static void, and we'll call that, we'll keep the naming similar so that we know what that is. Let's go with our sort of more standard naming convention for that one. And we're going to create an implementation method for that as well. So that will be returning nothing. DSI IO write command. And let's just copy and paste these guys. Also going to need to pass those parameters over as well, like so. Pop those in there. Alright. So essentially what will happen is the driver will call this method, which is going to then access this static method within the class, which is then going to access this implementation method, which may seem a little bit convoluted, but again, because we want to use a singleton class for this, it's potentially going to be the best way to make that happen for the moment. Now, without making things too confusing. So this will be QAD underscore LTDC imp DSI IO write command. And this will be where the command is actually getting written. Find the particular bit that I'm looking for, that'll be that one there. Okay. Now, depending on how many parameters the driver is wanting to send, so if it's less than or equal to 1, we're going to take one approach. Also, we'll take a slightly different one. So if it's just 1, we're going to just do a DSI short write. We'll need our DSI handle. Like so, otherwise we are going to want to do a long write. In which case it also needs to know how many parameters it's getting handed. To see the stream is behaving. Only taken 6 episodes, but I think The stream setup is working quite well now, which I'm pretty happy about. And I also need to, just because I fixed up the name for that one, we'll jump in here and fix that up in here as well. There should be num params. Okay. So that's that bit there, and then we need to link this guy up so it knows to call the method from the class instance. That one there. So now we're going to go with that one and that one. So the driver will call this method, which will then call the static method in here, which then calls our implementation method. Again, might seem a little bit convoluted, but allows us to implement that singleton class in order for that to all work correctly. So now that we've got that done, we can actually go through and tell the driver to initialize itself, or to initialize the LCD controller for the screen, which will be STM3209A controller. So the space in there. For that one, we're going to need to go OTM8009A init, which is the method we were looking at inside the OTM driver H file, header file. OTM8009A. Let it know what format we want, which will be RGB 888. OTM 8009A, and we need to let it know what orientation we're going to be using, which in this case will be a landscape. Like so. Now, what we might also do in our class, just keep track of whether or not we are actually initialized as well. And for that, we're going to use a QA init state. Just call that m_e init state. In our default constructor, we are just going to set that to QA not initialized, like so. Alright, so that's got all of our initialization done. Haven't done any of the de-initialization yet, so let's get that sorted out as well. And just before we get on to that and see if we can get some output from the display, I might just take a quick bio break, so I shall return in a couple of minutes. And we're back. All right, so let's get our de-initialization done. Now, thankfully, there's not as much stuff that's going to have to be de-initialized, or it's not quite as complex as it is to get it initialized in the first place. There is a few steps that we're going to have to go through, though, basically to make sure that things are back to where they need to be at the end of the de-initialization. So first things first, we're going to need to disable the DSI. That'll be HAL DSI stop. Pass it the handle for that one. I'll turn off our LTDC layers. Using HAL LTDC layer disable. Now, need to pass that this will be our DSI handle. Make sure we get these correct. This will be our LTDC handle. So might do layer 1, then layer 0. I like to try and do things in the opposite order in the de-initialization than I would during the actual initialization. I need to de-initialize the LTDC. LTDC, de-init. Actually, HAL has a capital I in there for that one. Pass it the handle for that. Now de-init the DSI. Now, a little bit curious, sometimes I will go through and actually set up the DSI and LTDC interrupts as well. However, I'm not sure that we actually need to do that, so we might try it without that first up and see how we go. Need to disable our clocks. Should be HAL RCC DSI clock disable. And don't need to pass that one anything, and also do the same thing for our LTDC. Then we're going to go through and reset the controller as well. Now we can just copy and paste that from here because we're going to use the same process as we did up there for our initialization as well. Right, so now certain methods for this class that I'm not sure that we're going to do in this episode. There is a few more that I want to do to get the LCD turned on, turned off, and set the brightness for it as well. So we'll get those guys done. And then see if we can get something showing up on the screen. As long as we can do that, we might call it a day on that one. And then as far as getting access to the actual layers and things like that, we might look at that in the next episode. The LTDC is going to be one of possibly the biggest driver that we're going to be writing. I think the audio driver tends to be fairly sizable as well, but probably not as big as this one, due to the fact that we've got to get the layers and a couple of different peripherals and things like that set up for this. So let's break this up a bit. Call these initialization methods. And let's let's call these guys control methods. Now for these ones, we are going to want some static methods, and let's call it LCD on. Don't need to pass it anything. Don't need to, don't know why we're actually putting returns in here because we're not returning anything. Like so, fix those guys up, and these will be imp LCD on. LCD off. And call this one set brightness. Pass it a uint8t. That lets it know how bright we want the screen to be. And we need to pass it that value as well. Alright, that's those three there. And we'll create these guys in here as well. Imp LCD on, void imp, there'll be a void in there, LCD off, and imp set brightness, N8T view brightness, like so. Just copy those and we'll pop those over in here. QAD LTDC control methods. Get these guys set up correctly so the compiler knows what they belong to. This guy, pop them in there and in there. Set brightness, imp LCD off, and imp LCD on. Now these ones are done by sending a DSI command to the controller. So I'm just going to do a short right there, supply it with the DSI handle. It's also going to need to know what our virtual channel ID is that we put in our config when we did our initialization. So that'll be virtual channel ID and DSI DCS short packet write P1, and then OTM8009A CMD disp on, which comes from our OTM8009A driver header file, like so. I'm going to copy and paste this into here and change this one to disp off. And we might also do it so that when we turn the display on, this is when we enable our backlight as well. So QAD LTDC backlight port, QAD LTDC backlight pin, and GPIO pin set to turn the backlight on. Copy and paste that guy, and we'll go with reset to turn the backlight back off. Now I'm also going to use a short right to the controller to adjust the brightness. So This one, we don't need to set what the virtual channel ID is. I'm just going to go with 0 for that one. It's going to be a short packet write. The particular command that we're going to be sending there will be cmd wr dis bv, and send it in uint16t. So I'm just going to typecast this, go with u brightness times 255 divided by 100, which will give the controller the correct value to be able to control that for us. So that's those guys done. Just make sure I'm not missing anything. So we've got our control methods, got all of our initialization and de-initialization done. We may be good to go. Alright, so in our main.cpp, we'll do this after doing our serial stuff. And again, most of this stuff in here, we're actually going to change at a later date. This is more just for testing the drivers and stuff at the moment. So initialize LTDC. Let's go if LTDC QAD LTDC. And before we're going to do that, we're also going to need to include the driver as well. So QAD LTDC.hpp there. Jump in here. We want to initialize that. Not going to need to pass it anything for the moment. And what we might also do is utilize our serial to let us know whether or not that is actually initializing correctly as well. So let's go serial uart tx string cr ltdc initialized. Initialization failed. So if it returns okay, we know it's working. If it doesn't, then this way we're going to get some feedback about that. Now, if it passes, we want to turn the LCD on. We should have saved that file. That might help. LCD on. And we might set our brightness to, let's try 10. But turn the brightness all the way up. It's not going to look great on the camera. If the camera actually wants to behave itself. Maybe. Let's find out. See if this builds for us. 8 errors. What do we got? Let's go to XD and we'll replace that with QAD. It's probably going to be all of those errors having the same issue. Let's find out. Camera doesn't want to behave itself for us. Okay, 5 errors. Let's see what we've got. Aha, made the same mistake again. So, need to let it know what it belongs to. We've done that for our command methods, but we've got fix those up so they should be right pin, and maybe it will compile. The camera doesn't seem to like being connected to OBS for long periods of time. It's a bad habit of dropping out. Still 5 errors. There's the error in here. Okay. Let's see why it is doing that. Aha, okay. So let's just go through and do a find and replace. 9A IO delay. Let's replace that just with HAL delay. That should sort that problem out for us. One warning. Where's our warning at? In here. Okay. I'm going to need to include something for that to behave itself, maybe. Yeah. So just so it can see that one, we'll go with STM32 F7XX.H. Should get rid of that warning. Wonderful. All right. Be nice if the drivers were coded a bit better in the first place, I think. 0 errors, 0 warnings. Let's see if we can actually get an LCD up and running. Now, we do actually have an image. However, because the sorry, brain's not working. Because the memory that the LTDC is using has not been cleared yet, we are going to get a strange pattern just from the particular data that's in memory. So let's show you what we're actually getting. So that one is not updating properly, but if we jump to this one, we can actually see right there. So a bit hard to see with the lights, but you can actually see that pattern that's on the screen. So we are actually getting the blue background color there, but you can see that weird horizontal and vertical sort of striped pattern that we're getting there. That's just because of the contents of the SDRAM at that particular point in time. but we'll call that a win for the moment because we know that the LCD is actually initializing correctly. And we are actually getting some stuff showing up. The fact that we're actually getting those patterns showing up on the display do show us that things are working correctly, even if we're not getting nice images showing up for the moment. So what we might do is call it a day for that one. And in the next episode, we'll go through and get the particular methods written for that driver so that we can get access to the frame buffers, and we'll start to write some of the rendering code so that we can actually get some of the things that we want drawn to the screen as well, and actually start to get some images on there. So as mentioned, this is probably the biggest driver that we're going to write, so it is a little bit more of a challenge than any of what we've looked at so far. Certainly a lot bigger than either the GPIO or FMC driver. Hope you have found this interesting anyway. As mentioned, this code will be up on GitHub shortly after this stream ends as well. I'll get that put up there. I'll pop some links in the descriptions both on Twitch and YouTube. If you did find it interesting, I'd love it if you follow the channel on Twitch, and if you're on YouTube watching it there, if you jump on there and hit like, hit subscribe, definitely helps with the inspiration moving forward to see that bit of feedback from people. So again, any questions, comments, anything like that, feel free to leave those either on the video or jump on our subreddit r/ones and zeros and leave a comment there if you like, or there is also the email address, and those details will be coming up shortly anyway. So thank you for watching, and hope you have a wonderful day or night or evening or whatever it is where you are. Thanks for watching.